Можно начинать, да? Угу. Так, ну давайте сначала определимся с языком. Let's first choose the language. Is there anybody here who prefers me to speak English? Okay. Okay, then the lectures will be in English. First of all, let me write my contacts. So my name is Pirkovskii. Here's my email and my office number 308. Okay, so to begin with, let's discuss some facts from the history of the subject, of the theory of topological vector spaces. The theory of topological vector spaces is a part of functional analysis, which was founded after the Second World War. Well, not more exactly, the first results on topological vector spaces were obtained by Banach and Kolmogorov already in the 1960s. But a systematic study of topological vector spaces began in the second half of the 1940s by Dieudonné, Schwarz, later Grothendieck, McKee, Kyoto, and many other brilliant mathematicians. There are also a couple of important papers by Bourbaki on topological vector spaces, and one quite influential monograph by Bourbaki. But actually, of the whole Bourbaki group, only Dieudonné and Schwarz, and later Grothendieck, worked in topological vector spaces. By the way, there is a funny story of how Grothendieck began to study topological vector spaces. So once a young man approached Dieudonné and said, "Professor, I want to be a PhD student." "Well, okay," said Dieudonné, "take my joint paper with Laurent Schwarz, read it. At the end of the paper, you'll see a list of open problems. Well, try to think about these problems." "Okay," answered the young man, who was Grothendieck, and disappeared. He disappeared for about a year. So Dieudonné even thought that, well, maybe the young man was frightened by the difficult problems and maybe he's chosen another supervisor. But eventually Grothendieck came back to Dieudonné. "Okay, my dear friend," said Dieudonné, "have you read the paper?" "Yes, professor." "And have you tried to solve the problems?" "Yes, professor." "So how many problems have you solved?" "I solved all of them, professor." And the legend says that this was a turning point in Dieudonné's mathematical career. So after that, he almost stopped his own research and devoted himself entirely to Grothendieck. So first Dieudonné supervised Grothendieck's research, then they worked together, and later, when Grothendieck decided to leave functional analysis for algebraic geometry, Dieudonné followed him. Probably the main contribution of Grothendieck to the theory of topological vector spaces is a very rich and powerful theory of topological tensor products and nuclear spaces. Grothendieck himself, he qualified his contribution to functional analysis as very modest. Well, indeed, probably his contribution to functional analysis is indeed much smaller than his contribution to algebraic geometry, which is really enormous. But nevertheless, Grothendieck's work on topological tensor products and nuclear spaces had a very strong impact on the development of functional analysis. By the way, it's quite interesting to look at the number of citations of Grothendieck's work. The number of citations of his PhD thesis devoted to topological vector spaces is almost twice as big as the number of citations of his joint book with Dieudonné, Éléments de Géométrie Algébrique, Elements of Algebraic Geometry. So it shows that the contribution of Grothendieck to functional analysis is really very important. Well, the golden age of topological vector spaces was roughly in the 1950s, 1960s. After that, starting from the 1970s, the interest of the mathematicians in topological vector spaces began to decrease. But nevertheless, one shouldn't think that this theory has died. This is very far from the truth. The theory of topological vector spaces is still alive. It is still evolving nowadays. But its development is directed maybe not so much towards general theory of topological vector spaces as towards applications in neighboring fields of mathematics. Chronologically, the first areas of applications of topological vector spaces were in partial differential equations and in distribution theory. And later, some important and useful applications were found in complex analytic geometry, in non-commutative geometry, and in quantum group theory. So I hope that we'll have some time at the end of the course to discuss at least some of the applications of topological vector spaces. Well, maybe that's all I wanted to tell you about the history. Now let's give some general definitions. We will work over the field of real numbers or over the field of complex numbers, and in most cases it will be inessential for us which of them is our base field. So let's denote any of them by a bold key. So bold key is our base field, and this is either the field of real numbers or the field of complex numbers. By definition, a topological vector space TVS for short, is a pair consisting of a vector space X. X is a vector space over K, and 2 is a topology on X. And we require that the topology must be compatible with the vector space structure in the sense that the algebraic operations, and we have 2 operations on a vector space, the sum and the multiplication by scalars, so they have to be continuous. Topological vector spaces form a category, and natural morphisms are continuous linear maps. So we will use the following notation. If X and Y are 2 topological vector spaces, then the set of all continuous linear maps from X to Y will be denoted by script L. This is the set of all continuous linear maps from X to Y. And in the special case where Y is our base field, so we get the space of continuous linear functionals, we get the so-called dual space of X, which is denoted by X prime. This is the dual of X. By the way, in the classical functional analysis, we normally use a different notation. We write x star here. But in the theory of topological vector spaces, it is common to write x prime. So I follow this tradition, and I use this notation for the dual. Well, it easily follows from the axioms that the topology on a topological vector space is shift invariant. This readily implies the following proposition. First of all, if you have two topological vector spaces x and y, then a linear map, say phi from x to y, is continuous, even only if it is continuous at 0. Or at any other point. The continuity at any point implies the continuity everywhere. And for more or less for the same reason, the set of all continuous linear maps from x to y is not just a set, but this is a vector subspace of the space of the vector space of all linear maps from x to y. This is quite easy, so this is an exercise for you. Okay, well, general topological vector spaces are actually too general to be interesting. So we will be interested in a rather special subclass of all topological vector spaces. Before we define them, let's recall what a seminorm is. Suppose that X is a vector space. Then a seminorm on X is a function P, a non-negative function P on X, such that it is subadditive, that is, satisfies the triangle inequality. And second, it is homogeneous in the following sense. So this equality holds for any x and any number lambda. So the only difference between a seminorm and a norm is that a norm is always positive on non-zero elements, and the seminorm can be zero at non-zero vectors. This is the only difference. A vector space equipped with a seminorm is called a seminormed space. And it's a simple exercise to show that a seminormed space is a topological vector space if we define the topology in exactly the same way as in the case of a normed space. Seminormed space is a topological vector space in a standard way. I don't repeat the details because, well, it's standard material. I'm assuming you know how to do this, how to define this topology in the case of a normed space, but in the case of a semi-normed space, the picture is exactly the same. We consider open balls, which are actually not balls geometrically because P is not necessarily a norm, but we define them in exactly the same way as in the case of a normed space, and they generate, they form a base of a certain topology. But of course there are many other natural examples of topological vector spaces, and we'll discuss them fairly soon. Okay, so now suppose that we have a whole family of seminorms of vector space on a certain vector space. In this case, we say that we have a polynorm space. For definition, a polynorm space is a pair consisting of a vector space X. X is a vector space, and P is a family of seminorms. On X. A family is not necessarily finite, not necessarily countable, just an arbitrary family of seminorms. Well, now let's observe that each polynorm space also has a natural topology. Let's introduce some notation. If X is a vector space and P is a seminorm of X, and X is a point in X and epsilon is a positive number, then we denote by a U P epsilon of X the set of those points Y for which P of Y minus X is less than epsilon. And we call it the open bowl. Centered at X of radius epsilon, corresponding to the seminorm P. Well, strictly speaking, I should use the quotation marks here, because so far we don't have any topology. We have just a vector space equipped with a seminorm. Nevertheless, it looks like an open bowl. And we define the closed bowl in a similar way, but now the inequality is less than or equal to epsilon. And we call it the open bowl, or the closed bowl. The closed bowl centered at X of radius epsilon. And in the case where the center is 0 and the radius is 1, we will write just UP. So this is the open bowl of radius 1 centered at 0. And similarly UP bar is the closed bowl of radius 1 centered at 0. Okay, now let's come back to our definition. Suppose that we have a polynomial space. And then we can define a topology on X in the following way. If XP is a polynomial space, then we define the topology on X generated by P to be the topology as denoted by tau of P whose subbase consists of all open bowls. So we take the family of all open bowls, UP epsilon of X, where little p runs over our family big P, X runs over X, and epsilon runs over all positive numbers. So we consider the collection of all such open bowls, and we generate the topology as shown here. So formally, if we now recall what a subbase is, so we must add finite intersections of all open balls. And finite intersections form a base of the topology. So an arbitrary open set will be an arbitrary union of basic open sets, where a basic open set is a finite intersection of open balls. Okay, well, now we see that our previous terminology is consistent, so the open balls are really open for this topology. And the closed balls are closed, and moreover we have the following simple exercise. If we have a polynomial space, then the closed ball, this set, is actually the closure. It's the closure of the open ball. In the topology 12P. And this is true for any x, for any p in our family, and for every positive epsilon. So the open ball is open and the closed ball is closed. Okay, so every polynomial space is a topological space in a natural way. But is it a topological vector space? The answer is yes. I have the following proposition. If we start with a polynomial space, and if we equip it with the topology generated by P, then we get a topological vector space. So the point is that the algebraic operations are continuous for this topology. The proof is a rather simple exercise for you. The only point I'd like to stress is that, of course, this property can be checked directly. You can directly show that the operations are continuous. But in my view, the most conceptual way of proving this is to observe that the topology on X is a special case of an initial topology, and to reduce everything to the case of semi-norm space. So a hint, reduce to the case of semi-norm space. And use the following trick. So for any semi-norm in our family, let xp denote the space act equipped with a single semi-norm p. So we forget about all other semi-norms from the family and keep only one of them. And we get a semi-norm space. Clearly we have a map, that's denoted by IP, from x to xp. This is just the identity map from this theoretical point of view, but format is not the identity map because the topologies here and here are different. Here the topology is generated by all semi-norms from our family, and here the topology is generated by only one of them. So I claim that if Y is a topological space, then a map f from y to x is continuous, if and only if the composition of f and ip, which acts from y to xp, is continuous for every p. For every p. So in other words, the topology on X generated by P is a special case of an initial topology. It has this property, and by using this property we can easily reduce the continuity of algebraic operations in X to the continuity of algebraic operations in the respective semi-norm spaces. So this is the end for the hint. Okay, so every polynomial space becomes a topological vector space in a natural way. And it is exactly this type of topological vector spaces that we are interested in. We will see soon that there is also a geometric characterization of such spaces within the class of all topological vector spaces. But before we give such a geometric characterization, let's briefly discuss some advantages of this class of spaces. One of the obvious advantages is that when we work with such spaces, we have two equivalent languages at our disposal. The first language is the language of general topology, of open sets, neighborhoods, and so on. And the second equivalent language is the language of seminorms and, let's say, inequalities between seminorms. And this is quite useful. Two languages are always better than one. Let's look at some simple illustrations. So suppose that we have a polynomial space equipped with the respective topology. When is it Hausdorff? It turns out that it is Hausdorff if and only if for any non-zero element x in our space there is a seminorm P in our family such that P of x is not zero, is strictly positive. Well, why is it so? This is very easy. If it is Hausdorff, and if we assume that this property fails, then well, there is an element x such that all seminorms from P vanish at x, but this really implies that x belongs to every neighborhood of 0. So otherwise, if this property fails, then x belongs to every neighborhood of 0. And of course, such a space is not Hausdorff. And to prove the right to left implication, we take two distinct points, x and y, and find a seminorm such that P of x minus y is positive. That's denoted by D. So this is a positive number. And then the triangle inequality really implies that we can easily construct two disjoint neighborhoods corresponding to P of radius D over 2 of x and of y. So these two neighborhoods are easily seen to be disjoint. And that's it. So this shows that the space is Hausdorff.
Can we let the norm be negative?
Excuse me?
I mean, what if P of x is all less than 0? I think so.
No, P is always non-negative. Well, where's the definition? When we define a seminorm, we always require that the seminorm is non-negative. So the seminorm is always non-negative. If it is non-zero, then it is positive. So it is positive, and we just consider two little balls, and the triangle inequality easily implies that they are disjoint. Okay, in our illustration, how can we describe convergence in the language of seminorms? This is also very easy. A sequence xn converges to an element x in the topology tau of P, if and only if it converges with respect to any seminorm. P of xn minus x goes to 0 for each P. Well, this is an easy exercise. Okay, let's now look at some concrete examples of polynorm spaces. The first example is the space of all functions on an arbitrary set. K to the power x, where x is a set, the set of all functions on x. Here X is any set. The standard topology on this space is defined as follows. For every point in X, we define a seminorm. It will be denoted like this. By the way, when we speak of seminorms, sometimes we will use we will denote them by Latin letters, such as P, Q, R, and so on. But sometimes we denote seminorms like norms, but equipped with suitable indices. So sometimes this is convenient. So we define a seminorm indexed by X on our space by the following simple formula. If f is a function, then we just take the absolute value of f of x. And clearly this is a seminorm. The standard topology, the topology given by the family of all such seminorms, is called the topology of pointwise convergence. The family of all seminorms of this form generates the topology of pointwise convergence. On the space of all k-valued functions on X. Why is it so called? Well, if we use this proposition, we easily see that a sequence Fn converges to F in our space, even only if it converges pointwise. This explains the name for this topology for every X. And it's a very simple exercise to observe that actually the topology of pointwise convergence is identical to the product topology on the space. This topology is the same as the product topology. The next example is the space of continuous functions on a topological space. So we consider the space of continuous functions on any topological space X. Here the standard topology is defined as follows. For every compact set K in X, we define a seminorm indexed by K on the space of continuous functions as follows. If f is a continuous function, then we take the supremum of f of x, of the absolute value of f of x, over K. This is finite because the function is continuous. And it easily seems to be a seminorm on C of x. And if we now consider the family of all such seminorms indexed by compact sets, then the respective topology generated by this family is called the topology of compact convergence. So it generates the topology of compact convergence. And in fact, this is a special case of the so-called compact open topology, which can be defined on the space of all continuous maps from X to any other topological space. Well, why is it called the topology of compact convergence? Well, again, if we look at this simple proposition, we see that a sequence of functions, a sequence of continuous functions, fn, converges to a function f in the space C of x, if and only if it converges uniformly on every compact set. So the double arrow denotes the uniform convergence, and this convergence is uniform for every compact subset K of x. So this is the standard topology on the space of continuous functions. In the case where x is compact, we get a very classical object of functional analysis, the Banach space of continuous functions equipped with a supremum norm. It's easily seen that if in the case where x is compact, we don't need to consider any smaller compact sets. We can keep only one of them, the whole x, and this topology is generated by a single norm. But in the case where x is not compact, we have to use the whole family of semi-norms. Example 3 is the space of smooth functions on the closed interval, say from A to B. Here the standard topology is defined as follows. So for each non-negative integer n, we define a semi-norm indexed by n on our space as follows. This will be the supremum of the f derivative of f over the interval AB. So we have a countable family of semi-norms. If n is 0, then this is just the supremum norm over the interval. So the standard topology on the space of smooth functions on the interval is the topology generated by this countable family of semi-norms. The standard topology on C infinity of AB is generated by all such semi-norms over all non-negative integers n. And again, if we look at the conversions and we use this proposition, we see that a sequence, say fk, converges to f in this space if and only if all partial derivatives converge uniformly. Okay, so this is the space of smooth functions on the interval, on the closed interval. Let's now look at a slightly different case, namely on the space of smooth functions on an open set. This will be example 4. So we'll consider the space C infinity of U, where U is an open subset of Rn. To define topology on this space, to define a family of semi-norms, it's convenient to use the standard multi-index notation. So if alpha is a multi-index, that is an untuple of non-negative integers, and if f is a smooth function on U, we denote by d alpha of f the following partial derivative of f here. The absolute value of alpha is just the sum alpha 1 plus alpha 2 up to alpha n. And now we define a family of seminorms as follows. For every compact subset K of U, and for every multi-index alpha, we define a seminorm indexed by K and alpha on our space C infinity of U as follows. If f is a smooth function, then we take the supremum over K of the respective partial derivative of f, supremum of d alpha f of x over K. So obviously this is a seminorm on our space, and the family of all such seminorms generates the standard topology. The standard topology on C infinity of U is the topology generated by all seminorms of this form over all compact subsets K and over all multi-indices alpha. It's a useful exercise to extend two previous examples to the case of smooth functions on an arbitrary manifold. Define a standard topology on C infinity of M, where M is a smooth manifold. Another important space, another important topological vector space is the space of holomorphic functions. Example 5. The space of holomorphic functions will denote it by O of U, where U is an open subset of Cn. If you don't know what a function or what a holomorphic function of several variables is, you may assume that n equals 1. Here the standard topology is just the topology induced from C of U, from the space of continuous functions. Standard topology on the space of holomorphic functions is the topology of compact convergence. Induced from C of U. And equivalently, we can induce a topology from the space of smooth functions. It turns out that we will get the same topology. This is, again, an exercise for you. This topology on O of U is identical to the topology induced from C infinity of U. Another important example is the famous Schwarz space. This is example 6. The Schwarz space is a very important object in mathematical physics and in harmonic analysis and in distribution theory. It is denoted by script S of Rn, and it consists of those smooth functions phi on Rn such that the function x to the power alpha multiplied by an arbitrary partial derivative of phi is bounded. For every pair of multi-indices alpha and beta. Here x to the power alpha is just a monomial. X to the power alpha is the respective monomial. xn to alpha n, x1 to alpha n, 1, xn to alpha n. So roughly this condition means that both phi and all its partial derivatives are very rapidly decreasing at infinity. To define the topology on the space, we just take the supremum of this function for every pair of multi-indices. So for every pair of multi-indices alpha and beta, we define a seminorm indexed by alpha and beta on the Schwarz space by the following simple formula. This is just the supremum over Rn of this function. And this standard topology on the Schwarz space is just the topology generated by the family of all such seminorms. In many books, you will find rather different families of seminorms generating the same topology on the Schwarz space, and this is normal. In fact, it's quite normal that if we take a vector space, there are many equivalent families of seminorms defining the standard topology on the space. Equivalent in the sense that the topologies generated by these different families are identical. We'll discuss this phenomenon a bit later, after we discuss continuous linear operators and equivalence of families of seminorms. Okay, another quite important example is example 7. This is kind of a discrete analog of the Schwarz space, the space of rapidly decreasing sequences. It is denoted by little s. The space consists of those sequences in k to the power m such that the following sequence xn multiplied by n to the power k is bounded for every non-negative integer k.
Is denoted by little s?
A little s, yeah. Well, little s is this a little analog of the Schwarz space. This is the way of remembering the notation. A little analog of the Schwarz space. The topology, again, is defined in a rather natural way. We just take the supremum of the sequence for every non-negative integer k. So for every non-negative integer k, we define a seminorm, which is actually a norm, by the way, a norm indexed by k on little s, to be the supremum of the respective sequence xn n to the power k. And this family generates the standard topology. The standard topology on S is generated by the respective sequence of norms indexed by natural by non-negative integers. At the first glance, this may seem rather inessential example, but in fact, this example is very important. It is important in general theory, in particular in the theory of nuclear spaces, but on the other hand, there are some results due to different mathematicians that many classical spaces, many classical topological vector spaces are actually isomorphic to S. For example, it turns out that the Schwarz space is isomorphic to S. This is not very hard, but this is true. And a harder result due to Dietmar-Vogt is that the space of smooth functions on any compact smooth manifold is actually topologically isomorphic to little s. And there are some other results of the same nature. So this example is quite important. The last two examples are maybe you probably know about them from your functional analysis course. Example 8. If X is any topological vector space, then for every continuous linear functional f on X, we can define a semi-norm indexed by f on X by the following formula. It's just the absolute value of f of X. And the family of all such semi-norms generates the so-called weak topology. The weak topology on X is the topology generated by all semi-norms of this form. And the standard exercise is to show that it is indeed weak in the sense that it is weaker, it is coarser than the original topology on X. And a similar example, a similar trick can be done with the dual space, example 8. Again, if X is any topological vector space, then for any element little x in X, we can define a semi-norm on the dual space by the following rule. And the topology generated by the family of such semi-norms, this will be the topology on X prime, is called the weak star topology. The weak star topology on X prime is the topology generated by all semi-norms of this form. And it's easily seen that this topology is identical to the topology induced from the space of all k-valued functions on X. The weak star topology induced from k to the power x, where k to the power x is equipped with the topology of pointwise convergence. Okay. Well, at this point, that's all I wanted to tell you about examples. Later we will meet some other important examples. And now our next goal will be to give a geometric characterization of polynormable topological vector spaces. When I say polynormable, I mean that spaces whose topology can be determined by a family of semi-norms. Before we can give such a characterization, let's discuss some some geometric notions related to convexity. Suppose that we have a vector space. X is a vector space. Just a vector space, so we don't assume any topology on X. And we give the following definition. We say that a subset S of X is, so definition 1, we'll have several definitions. Definition 1, we say that S is convex if for any pair of points x, y, S contains the closed interval, the closed interval from x to y. Where the closed interval is by definition the set of all such so-called convex combinations, Tx plus 1 minus Ty, where T is between 0 and 1. Definition 2, we say that S is circled or balanced if it is stable under multiplication by numbers of modules less than or equal to 1. If lambda S is contained in S for every lambda such that the absolute value of lambda is less than or equal to 1. Yeah, circle, in Russian circle is закругленная. Закругленная. Balanced is уравновешенная. So there are two kinds of terminology. I prefer to say circled because this word better corresponds to the case where the base field is the field of complex numbers. And I like complex numbers more than real numbers. Well, it's clear because why is it called circle? Because in this case, the set of all such lambda form the disk, the unit disk on the complex plane. And the word balanced is better describes the situation in the case where we work over the real numbers, because in this case lambda runs over the interval from -1 to 1, and this property is indeed, from a physical point of view, something like the property that S is balanced in some usual sense of the word. Okay, and property 3, we say that S is absolutely convex. Absolutely convex if it is both convex and circled. Convex and circled. Well, it's easily seen that the intersection of any family of convex sets is convex. The intersection of any family of circled sets is circled, and therefore the intersection of any family of absolutely convex sets is absolutely convex. And this leads naturally to the following definition. The convex whole of a set S in X is the intersection of all convex subsets T of X containing S. And this is just the smallest convex set containing S. similar way, we can define the circled hull and the absolutely convex hull of S. Circle hull and the absolutely convex hull, which is traditionally denoted by gamma of S. They are defined similarly. These hulls can also be described explicitly as follows. This is an exercise for you. The convex hull consists of all so-called convex combinations of the following form: lambda I xi, so we take all such finite sums where the elements xi are in S, and lambda I are non-negative numbers such that the sum of lambda I is 1. This is the convex hull. The circled hull is very easy to describe. It consists of all elements of the form lambda x, where x runs over S, and lambda, the absolute value of lambda is less than or equal to 1. And finally, the absolutely convex hull, gamma of S, consists of all linear combinations lambda I xi, where xi are in S, and lambda I are arbitrary numbers from K such that the sum of their absolute values is less than or equal to 1. This is an explicit description for gamma of S, for the absolutely convex hull. Well, this is a useful exercise for you. And as a corollary, we see, for example, that if S is circled, then so is the convex hull. The convex hull of a circle set is circled. S is circled implies that convex hull is also circled. And this observation easily implies that gamma of S, the absolutely convex hull, can be expressed in the following way. This is the convex hull of the circled hull of S. Clearly the right-hand side is contained in the left-hand side, but on the other hand, part 1 implies that the right-hand side is absolutely convex, and this implies that they are the same. Okay, now suppose that we have two sets, S and T. We say that S is absorbed by T, or when T absorbs S, if there exists a constant C, and a negative constant C, such that S is contained in lambda T whenever the absolute value of lambda is less than or equal to C. In other words, S is, roughly this means that S will be contained in T after we blow it up. In a special case where T is circled, we can simplify this definition. Let's observe, well, this is a very simple exercise. If T is circled, then S is absorbed by T, and in this case we use, well, let's introduce the respective notation. So S is observed by T if and only if there exists a non-negative lambda such that S is contained in lambda T. So in the case where T is circled, this definition can be simplified like this. Okay, our next definition, we say that a subset S of T, of f of x, a subset f of x is absorbing if it observes every point. For every x. In Russian this is поглощающее. Поглощающее множество. A typical example of an observing set is a neighborhood of 0 in any topological vector space. A neighborhood of 0 in a topological vector space, X is absorbing. Well, why is it so? This is so because X belongs to lambda U. So if we want to show that it is absorbing, we must show that for every X there exists a constant C such that this property holds if lambda is bigger than C. But this property can be written in the following way. Lambda inverse X belongs to U. And this is true for large lambda because the multiplication by scalars is continuous. If we multiply X by a little number, then by continuity of the multiplication, the result will be in our neighborhood of 0. So if lambda is big, then lambda inverse is small, and this will be in U. So any neighborhood of 0 is absorbing. Now, given any absorbing set in any vector space, we can define a useful function, which is called the Pirkovskii functional. So we suppose that X is a vector space, and S is an absorbing subset of X. The Pirkovskii functional of S is the following function. It is denoted by PS. It is non-negative, and it is given by the following formula. PS of X is the infimum of those lambda non-negative for which X belongs to lambda S. Since S is assumed to be absorbing, we see that this set is non-empty. The set is always non-empty, and we can take the infimum. Well, so what can we say about the Pirkovskii functional? Let's look at some general properties of this function. A proposition. First of all, PS of lambda X is lambda PS of X for every non-zero lambda. That is, the Pirkovskii functional is always positive homogeneous. Property 2, if S is convex, then the Minkowski functional is subadditive. It satisfies the triangle inequality. Property 3, which is actually a combination of, oh no, sorry, this is not yet a combination. Property 3 is that if f is circled, if S is circled, then PS of lambda x is equal to the absolute value of lambda times PS of x, and this is true for any number lambda, for any lambda in K, and for every x. And 4 is a combination of 2 and 3. If S is absolutely convex, then PS is a seminorm. If S is absolutely convex, then PS is a seminorm. And in this case, we have the following conclusion. The open unit ball corresponding to PS, corresponding to this seminorm, is contained in S, and S is contained in the closed unit ball corresponding to PS. So S sits in between the open ball and the closed ball, corresponding to the Minkowski function. Well, I will not prove part 1. This is more or less immediate from the definition. Let's prove part 2. This is also immediate, or almost immediate from the definition, but requires some tricks. Where is the definition? This is the definition. So first of all, let's draw a picture. So suppose this is PS of x. This is 0. So since PS of x is the infimum of the set, for each positive epsilon we can find an element lambda here, such that x belongs to lambda x, and lambda is almost equal to PS of x. Formally, for each positive epsilon, we can find lambda such that x belongs to lambda s, and such that lambda is almost PS of x in the sense that lambda is smaller than PS of x plus epsilon. And similarly, we can find a number mu such that x belongs to mu s, and such that mu is smaller than PS of y. Sorry, y belongs to mu s, and mu is less than PS of y plus epsilon, just by the definition of PS. So now we see that x plus y belongs to lambda s plus mu s. And now we use the convexity. By convexity, we see that this is equal to lambda plus mu s. This is true by the convexity of S. And that's it. So now x plus y belongs to the set. We look again at the definition of the Minkowski functional, and we conclude that PS of x plus y is less than or equal to lambda plus mu, which is smaller than PS of x plus PS of y plus 2 epsilon. And since this is true for every positive epsilon, we get our subadditivity. Okay, so part 3 is an exercise for you. And finally, part 4, Well, the statement that P as a semi-norm is immediate from 2 and 3. And as for the inclusions, well, the second inclusion is again clear from the definition. If x belongs to S, then we see that lambda equals 1 sits in the set, and so the infimum is less than or equal to 1. So our element sits in the respective closed ball. And to get the opposite inclusion, if now x sits in the open unit ball, then this number Ps of x is less than 1, and we can find lambda which is still less than 1 and is such that x belongs to lambda s. But this means that this lambda inverse x belongs to S. But S was assumed to be circled, so we can multiply now this by lambda, and this implies that x belongs to S. And so the open unit ball is contained in S. That's it. Okay, now I have to stop here. So this part of today's lecture, I mean the part which was devoted to notions related to convexity, is important for us because at the next lecture we start by showing that topological vector space is polynormable in the sense that its topology can be given by a family of semi-norms, even only if it is locally convex. Locally convex means that there exists a base of neighborhoods of 0 consisting of convex sets. So this is a very useful geometric characterization of polynormable spaces.
С листочками у вас все точно так же работает, как обычно.
Да, с листочками как обычно.
И вы снова на этот полугодовый сайт будете кидать?
Ну, там я сделаю страничку. So I'm going to, I'll make a web page of the course, and I'll put there, sometimes I'll put there exercise sheets, which are not obligatory, but they're useful for you, because at the end of the course we'll have a take-home exam. So each of you will have a personal assignment and about 10 days to do it. And the assignment will consist of selected exercises which will be taken from the exercise sheets. So it is very useful to do these exercises. The link to the webpage of the course, I hope it will appear at the site of the department, well, maybe, I hope in a week. More than that in a few days.
Это будут те же самые, которые в прошлый раз.
Ну, модифицировано несколько. Я посмотрю, может, я там что-то добавлю, что-то уберу, но в общем примерно, да.
У меня вам как раз один сложный для внешнего курса.
Ну, то есть там, если вы сдадите здесь, то там вот за что, да?
Ну, типа того, там 5 внешних можно зачесть, а потом на 5.
А я почему-то думал, что вы уже слушали когда-то, нет?
Я его слушал, но мне что-то ближе к концу стало как-то сложно, и в итоге я поленился делать дизайн, все не пошло. Ну, я, кстати, мало что помню. Ну, то есть у меня почему-то ощущение, что это было где-то в середине, хотя на самом деле начинал.
Ну, в общем, что для того, что программируемость равносильно алгоритму? Да.
У меня почему-то в голове это было где-то в середине.
Нет, ну прям
Наверное, как раз в середине функционального образа.
Да, но там обычно схему рассказывают, но...
Ну да,
в принципе...
Я даже что-то не помню.
Ну, функциональный анализ обычно заверяют, что это полнорма, потому что вот проверить, что это полнорма. Ну там много чего пропускают.
Что-то было про какие-то аналогии?
Нет, аналогии
Это как раз тут, скорее
Нет,
всего.
в смысле, я говорю как раз, что я пытаюсь вспомнить, что тогда вообще было. Вот слово хронология запомнилось, что это автоматизация ограничена мной.
Это не здесь,
Ограниченность равносильно непрерывности. Да?
Ну это одно из эквивалентных определений.
Ну вот, да, ну смысл, главный смысл.
Ну, да.
Хотя я помню, что в конце просто что-то старое, какие-то исследования возникли, такие,
Ну, то есть, положение денег, я могу как раз расскажу.
Это самое, я что-то потом рассказываю, в каком порядке вы рассказываете то, что Грек рассказывает.
Нет, это не знаю. Ну, это, в общем, часть медицинского хода дела.
Ну ладно, ну что, это понятно. Есть точно, что светит?
знаешь, ты что?
Вот, и все заранее забивают места. То есть тут еще не начался, а уже места забили. Вот это популярно. Ну, слушай, на Лондона, когда я ходил, да, в Лондоне, у него не было такого, что все места забивали заранее. Но ходило тоже много людей. Нет, вообще-то, честно, мне про лингвиста тоже, я услышал, что какой-то крутой лингвист. Хотя и Лондон тоже был.
Ну, не знаю, мне...
А знаете, где вообще машину настроить?
Нет,
вы в курсе? Проект, в смысле. На втором походе Хотите меня проводить? Я первый раз один город.
Знаешь, что 50 человек, 50, это максимум. Такое количество, как и на основном сайте.